Here, let's try to look at an example of moving average process. Right, okay, this is a theory question. Let me omit it. Explain with reasons which ARIMA time series would fit the observed data in the charts below. Now, first of all, ACF, it's only we are seeing that it is a non-zero value only for the first lag. After the first lag, it is zero. So, which is a clear indicator of a moving average function. And just to convert, just to look at it, even the partial autocorrelation, it is gradually decaying to zero, which is even more strengthening my understanding that this kind of a graph is very much possible for an MA1 process. Right now, this is a theoretical aspect itself. Now consider the time series model given by this. I have xt is equal to alpha 1 xt minus 1 plus alpha 2 xt minus 2 plus beta 1 et minus 1 plus et. Now this is where, okay, this is a white noise with variance. So I need to find the Yule-Walker equations for this model. Now that ETs are there, I'll first take covariance of xt comma et. So et comma et, if I am taking, this is nothing but sigma squared. Then I can take covariance between xt comma et minus 1. So when I am doing this with this versus et minus 1, this is coming out as alpha 1 time the covariance between et minus 1 and xt minus 1 becomes sigma squared, plus here this is 0. Again I have here beta 1 times covariance between et minus 1 and et minus 1, even that is sigma squared. So it comes out to alpha 1 plus beta 1 times sigma squared. Then I can take the covariance between xt comma xt, which is the variance kind of stuff. I can take this as gamma 0, and here if I start going with alpha 1 times gamma 1, alpha 2 times gamma 2, so xt comma et minus 1 is going to be 0, right? The xt, okay, xt and et minus 1, we have already got it, alpha 1 plus beta 1 times sigma squared, and covariance between xt and et I have got it as sigma squared, that is gamma 0. Now when I do this the covariance between xt and xt minus 1, this entire thing with xt minus 1, so this comes out as alpha 1 covariance xt minus 1 is gamma 0 plus alpha 2 times gamma 1 plus beta 1 times covariance xt minus 1 and et minus 1, which is sigma squared itself. So beta 1 times sigma squared, and xt minus 1 and et does not exist. Similarly, for a time period lag 2, so I do it with xt minus 2. So this comes out as alpha 1 gamma 1 plus alpha 2 gamma 0, and beta 1 and beta 2, now with xt minus 2 they don't exist, so that part is 0. So I am getting gamma 2 is something like this. Similarly, I can do for gamma 3, gamma 4 kind of stuff, which means now if I try out for gamma 3 also, it becomes alpha 1 gamma 2 plus alpha 2 gamma 1. So it is coming out like gamma k is coming out as alpha 1 gamma k minus 2 plus alpha 2 gamma k minus 1 for k greater than 2. I am getting this as a general function. These are the different kinds of Yule-Walker equations that I am getting for this model. Whether the partial autocorrelation function for this model can give a 0 value. First of all, we have a beta time beta 1 times et minus 1. beta 1 value will be the modulus of the beta 1 value will be less than 1, but obviously it was not 0. So because of that, it keeps the error term keeps narrowing down, narrowing down, narrowing down, which means the partial autocorrelation will go closer to 0, but it will not touch 0. So you will find it forever, the partial autocorrelation function. It looks as if it is exponentially decaying out to 0, but it will never become 0 at all. Right? A simple way to solve this kind of expression.